Welcome to Kognito Key. What if I told you that inside every single living thing, there are these tiny, microscopic machines that actually make life possible? Well, they're called enzymes. And today, we're going to explore the really ingenious technique that lets us put these natural powerhouses to work on an industrial scale. So, here's what we've got on tap. First, we'll get into the big problems scientists had with these tiny machines. Then, we'll look at the super clever solution they came up with. After that, we'll check out the different ways it's done, weigh the pros and cons, and finally, I'll show you where this amazing science pops up in your everyday life.
All right, so what's the big dilemma? Well, it turns out that for all their power, enzymes have a couple of major weaknesses that make them surprisingly difficult to work with in the real world.
Okay, so here's the basics. Enzymes are nature's very own catalysts. What they do is they grab onto a substance, we call it a substrate, and help turn it into something totally new, a product. And the really cool part? The enzyme itself doesn't get used up. In theory, that means it can do its job again and again and again.
So that brings up a pretty big question, right? If these enzymes are so great, why aren't we just using them everywhere? Well, the problem is when they're just floating around freely in a liquid, they are a huge mess to deal with. It's really hard to separate them from the final product, they can be pretty unstable, and you lose a bunch of them in the process, which, you guessed it, makes everything incredibly expensive.
And this is where scientists came up with a really smart solution. They thought, hey, instead of letting these powerful little machines just float around wherever they want, what if we could give them an anchor, a permanent workstation? And that is the whole idea behind enzyme immobilization. We basically attach the enzyme to some kind of solid, non-reactive material, which we call a support. This acts like an anchor, holding the enzyme right where we want it. It can still do its job perfectly, but now it's not going to get washed away with everything else. So this whole process really just boils down to three main parts. First, you've got the enzyme itself, our little catalyst. Then you have the support matrix, that's the anchor. And finally, you have the mode of attachment, which is just the specific way we connect the two together. Now, you can't just use any old thing for this anchor. A good support has to check a lot of boxes. It needs to be strong, it needs to be stable, and it absolutely can't mess with the reaction. Oh, and it also has to be safe for biological systems, be reusable, and, of course, be cheap enough to use on a massive scale. No big deal, right? Okay, so how do we actually do it? How do we stick an enzyme to its support? Well, there are a few different methods, and each one has its own advantages. Let's do a quick tour of the main techniques. First up is adsorption. This one is the simplest, and it's been around the longest. All that happens here is the enzyme just kind of sticks to the surface of the support using weak physical forces. Think of it like a sock sticking to your sweater because of static cling. It's super easy and gentle on the enzyme, but that connection, well, it isn't very strong. All right, next we've got entrapment. Now, with this method, the enzymes aren't just stuck to the surface. They're physically trapped inside the little pores of a gel or a fiber. It's a lot like catching fish in a net. The enzymes are held in there really securely, but the catch is the substrate has to find its way into the net to get to them, and that can sometimes slow the whole reaction down. Now, if you want a much stronger connection, you use covalent binding. This method actually forms a strong chemical bond between the enzyme and the support. You can think of it like using superglue. This gives you a really robust connection, so there's no leakage. But the chemical process you use to make that bond can sometimes mess with the enzyme's activity a little bit. And finally, there's cross-linking. This one's pretty clever. It actually gets rid of the support matrix altogether. What you do here is bond the enzyme molecules directly to each other, so they form this big 3D clump. It's very stable, but the chemicals you need to use can be a bit harsh on the poor enzymes. So, you might be thinking, is immobilization the perfect flawless solution? Well, not quite. Like pretty much any technology out there, it has its good sides and its bad sides. So on the plus side, the biggest advantage is reusability. I mean, being able to use the enzymes again and again just slashes costs and makes everything so much simpler. And these anchored enzymes are often way more stable too. But on the downside, the process can sometimes reduce how well the enzyme works, the initial setup can be pretty pricey, and you always have to worry about microbes getting in and causing contamination. Now, I know this all might sound very technical, but you would be absolutely amazed at how much this technology actually impacts your day-to-day life. So let's take a look at where you can find it out in the real world. And here's something fun.
This is not a new idea at all. People were using really simple versions of this way back in the 1800s to make things like vinegar. But of course, it was really in the 1960s and 70s that the science properly took off, and that's what led to all the amazing ways we use it today. So where is all this stuff? Well, it's in the food industry, helping make things like high fructose corn syrup and some jellies. It's in medicine, used on diagnostic test strips and in fancy drug delivery systems. It helps make antibiotics, it cleans our wastewater, and yep, it's even in your laundry detergent, breaking down all those greasy stains. So the main takeaway here is that by giving nature's tiny machines a stable home, we've completely unlocked their potential for all these incredible applications. It really makes you wonder, now that we can anchor these enzymes and put them to work, what other fundamental biological process are we on the verge of figuring out how to use next? Thanks so much for joining us here on Kognito Key. If you enjoyed this explainer, please be sure to hit that like button, share it with a friend, and subscribe so you don't miss our next deep dive into the amazing science that's all around us. See you next time.